Okay, so the first lesson on the last topic we're going to be learning this bimester, and this semester actually is integral calculus. And today I'm going to give you an introduction to what this is. Very broadly speaking, integral calculus can be put in two different um, ways of studying it that they come together, but we kind of separate it in two parts. First, it's the definition of the integral, the notion of what is an integral through the history of the development of what this was, um, as it was done by Newton, Leibniz, the big names, the motivation behind it to obtain areas under curves, the later definition, mathematically speaking, rigorous definitions in terms of Riemann sums of theorems like the mean value theorem. That is like one part. And then there is always this other part on how do we get an integral. I'm calling these operative issues, and these include antiderivatives, how to obtain integrals, how to obtain indefinite and indefinite integrals, and there are many techniques of integration. They all come together in the fundamental theorem of calculus. This is kind of the thing that makes a bridge between these two parts. But for now, we're gonna just focus on the easiest one of them, antiderivatives. So let's begin. Antiderivatives are basically the opposite operation to the derivative. I'm going to be defining a new operation called antiderivative, and what the derivative does, the antiderivative undoes. That's basically it. It's like addition and subtraction, or multiplication and division. You have one operation and you have the inverse operation, the opposite operation. How does it work? Pretty much as the derivatives had rules, there are going to be rules for antiderivatives. So let's begin with the easiest one of them, power rule. Imagine that you have this, and the problem is to obtain the derivative of the function that you're looking at, 2x. So you have to assume that this is already the result of differentiation. This is already the derivative of some function. What was that function? That's what we're trying to get. If this is the derivative, what was the function that we were getting the derivative of? And this one is quite easy. You can see that it's x squared. If you were to differentiate this one to obtain the derivative of this, the 2 comes down, this one changes to 1, and we have this function. So pretty simple. What about this? 3x squared. Again, this is already the derivative of another function. So which function is that? Simple enough, x to the 3, because if you were to get the derivative of this, 3 comes down, this power of 3 becomes a power of 2, and you get these things. So we're just assuming that the functions we're given are already the result of differentiation, are already the derivatives of some of the functions, and we are looking for these other functions. What about this one? This one has two terms. It's a little bit more complicated. This part is quite easy. What functions, which functions, when you get the derivative of them, give you 1? Simple x. And x must have come from an x to the 2. But if you try to get the derivative of this one will give you the 1 that you need, but this one will give you 2x, which is not what you have. So this is not it. It needs to have some other coefficient so that when you multiply it, you actually obtain what you need, and in this case it's this one. If you get the derivative of this, the derivative of x is the 1, and the derivative of this thing, the 2 comes down, multiplies the 3, therefore you have a 6, and the power decreases by 1, and you have your x. So is there a formula, is there a way in which we can kind of put all this together and you wouldn't have to be thinking of what is the function that came before? Yep, of course there is. So the antiderivative of power functions like x to the n is going to be given by this fraction, x raised to the old power plus 1 and divided by that same number. Again, x raised to the old power plus 1 divided by the same number that you're putting as an exponent. Let's see how it works. Obtain the antiderivative of the following function, 3x to the 5. So, first step, the 3 as in the derivatives just stays there. You don't have to touch it, and you have to just work with the x's. So the old power is 5, we're going to increase that by 1, and we're going to divide it by that same number. 5 plus 1 is a 6, so we have this, and after you have this you can start simplifying stuff. This can be simplified to just this, and that's it. This is the antiderivative of this one. If you were to get the derivative of this function, you would actually obtain this function over there. What about this one? You have 3 terms. How do you apply this rule? Well, you apply it in the same way as the derivatives, term by term. So again, ignore the 4. X to the old power was 2, 2 plus 1, over the same number. Ignore the 6, and then it's x. Nothing's written here, which means that there is 1. So it's 1 plus 1 over the same number, minus 4. And if you have nothing written out here, it means that you have just x to the 0, because x to the 0 is 1. So you would formally have x to the 0 plus 1 over plus 0 plus 1. But after this, you would just need to remember that any number, when you're trying to get the antiderivative of a number, that just means putting an x next to it. And again, 2 plus 1, 3, 2 plus 1, 3, 1 plus 1, 2, 1 plus 1, 2. This is our function. Simplify it if you can. You can simplify this too, and we can write this without this one. That's it. This is the antiderivative of this function. If you get the derivative of this function, you obtain that. I want you to focus on this one, on this last result. So this function, using this rule, we obtain its antiderivative as this other function. And if you actually differentiate this one, if you get a derivative of this, you obtain this one. So no problems there. But what happens with these other two functions? They are basically the same, except for these numbers here. But remember, if you try to get the derivative of a number, that number becomes a 0. So this one will yield the same derivative, and this one will also give you the same derivative. So which one of these three is actually the correct antiderivative? As a matter of fact, you don't have only 3, you have an infinite number of functions, of possible functions, that when you differentiate them give you the same thing. You can put any number here, and when you get the derivative you will still get this function. So which one is it? This fact proves two things. One, getting antiderivatives is more complicated than just getting derivatives, and two, we're going to use this fact later on in some initial value problems. For now, this just means that our formula is incomplete. So whenever you're trying to get antiderivatives, because of this reason, you have to put a plus c. It's undeterminate up to a constant. So whatever function you get, just add plus c at the end.